The topic today is using advanced laws in CATIA Kinematics. I'm sure all of you must have used kinematics in the past, so you do know the basics, which is how to create commands, how to create joints, and this and that. I want to cover a separate topic, which is how to use laws. A couple of words about myself. I've been working with CATIA for, about 20 years now. I'm fairly good with it, so feel free to toss any question at me. I should be able to answer, I believe. So what it's all about, when you set up a mechanism in CATIA Kinematics with joints and stuff, you create commands. And for complex simulations, you might end up with several commands. The problem is that when you want to simulate a mechanism with commands, each command must be manipulated manually and independently. So if you look at this page, there's a bunch of sliders, and if I move any of those sliders, the command will be controlled, the value change, and the mechanism is moved. Because each slider has to be manipulated separately and independently. Using this option is very difficult, next to impossible, to model simultaneous movement of parts. And also, if you use a simulation on request, the only type of motion you can simulate is constant velocity, linear motion. That's about it. So what's the solution? Instead of using simulation with command, you can do simulation with laws. And the way how it works, you essentially link all your commands to a single parameter, time parameter. In CATIA mechanism, it has a name, kinematic time. So this way you control your entire mechanism by just one parameter, which is time. It makes it easy to move parts simultaneously. And also you can simulate variable velocity motion, such as parabolic acceleration or other options. So basically, you got to create this. You see there is a kinematic time, and in turn, it controls all the commands in your mechanism. Now, how you make that happen? Actually, there are several ways, several methods, and I'm going to go through each of those methods or the practices and workflows using examples. And I'm going to start with a very simple example, which is you can actually use formulas. And the example I'm going to show you in just a bit, I got a couple of prismatic joints, a couple of blocks, and I want to make my blocks move simultaneously at the same time, but with a different velocity. So the brown block is going to move with a velocity 10 millimeters per second over, let's say, 20-second time. And the blue block will move with a velocity, half of it, which is 5 millimeters per second over the same amount of time, which is 20 seconds. So because the motion is linear, we can describe the linear displacement or length d as v, which is velocity times time. And you can do it using simple formula. Okay. So my first example, let's take a look at it. Okay, that's not the one, this one. Okay, and you see there are two blocks, the brown and the blue one, and there's a mechanism here. Okay, and there are two commands. Okay, so if I simulate with the commands, it's pretty basic. As you see, if I drag one slider, it moves one block, and there is another slider that moves another block. Now I want to make them move with different velocity, with different speed. And I'm going to do that using formulas. So when I double click on a command, and when I right click in the command value field right here, you're going to see this option, edit formula. Okay. Let's click on it. So basically it tells me that's a command brown, which controls the brown block length equals what? So if you recall this formula, this is what we need to put in. So it's velocity times time, and the brown block is going to be moving with 10 millimeters per second. Okay, so it's going to be 10 millimeters divided by 1 second. That's the velocity times kinematic time. So I'm going to click on the mechanism. So as you see, there is a mechanism kin time parameter. As simple as that. Okay. And I'm going to do the same for the second block, which is the blue one. It should be half the velocity, right click, edit formula, and now it's going to be 5 millimeters per second times kinematic time. Okay, and we are done. So now instead of simulation with commands, we're going to click simulation with laws. Now it's controlled by the same time parameter, and I'll just run a quick simulation. You see that the first block starts moving, and the second block, as you see, it's traveling half the distance because it has the half speed. Maybe I'll make it a little faster. So I'll use, instead of 1,000 steps, about 200. Okay. So I see both blocks are moving, but actually I can control the velocity of each block. That's perhaps the easiest option using formulas, but what if I want to simulate a more complex motion? Which brings me to the second example. It's the same 2 blocks, just like that, driven by prismatic joints. And the brown block, that's how it's going to move. So it's going to go up by 200 millimeters in the first 25 seconds. Then it's going to stop and stay put for the next 25 seconds until 50-second mark. And then it's going to move down to the initial positions in the last 50 seconds. And total time is 100 seconds. As far as the blue block, it's going to experience a different kind of motion, okay? And it's going to stay put for the first 25 seconds when the brown block is moving up, so up to this point. Okay, so it stays put, and then it starts accelerating according to the parabolic law. Okay, so because it's a t squared, the velocity increases with the duration of time. So actually the block is accelerating, and that's the formula. So the length or the displacement which the block travels is 1/2 a, which is acceleration, times t squared. Well, to make that happen, I'm going to have to create 2D curves or sketches. Okay. So let me get rid of a couple of things here. I want to unlink my commands from the time using formulas. Okay. And when you deal with, let me, by the way, reset. Actually, I'll undo. I just want to bring the blocks back to the initial position. Okay, and gonna do that. Okay, initial position. I can get rid of the formulas. I'm just cleaning up after my first example. Okay, so you got to create 2-dimensional curves. The easiest way is to use a sketch. It doesn't have to be a sketch. Actually, it could be like a 3D curve if you like those, but the easiest option is probably using the sketch. So you start by creating a new part, okay, because the easiest way is to put those laws or curves into a separate part. So I'm going to click create new part. It's going to go here. Okay, I'll use the origin, and best of all, if you create those sketches at a location in your assembly which is away from the main assembly, so you can easily see the curves, you can visualize what's going to happen. And I'm going to go into that part. Okay, and I'll create a position sketch using a point. So I'm going to put a point, let's say, on this plane. That's going to be the origin. Okay, and I'll create position sketch. The plane is this one, and projection point, that's this point. Okay, so I'm a sketcher, and I need to sketch. The first one is going to be for the brown block. Okay, that's the law. So it should go up, stay put, and then go down again. Well, just a simple polyline. Okay, so it's going to go up, stay put, and then go down. Of course, I need to dimension it. So the maximum displacement was, I believe, 200 millimeters. So I'm going to change it to 200. Okay. No, that's not what I wanted. Okay, and add other dimensions. So there's going to be from here to here. That's 25. I'll change it in just a bit. Okay, and the last one from here to here. And of course, so there's my total duration is going to be 100 seconds. Okay, that's 50 seconds, and that's 25 seconds. So that's my two-dimensional curve for the first law, for the brown block. So the same way, I would create the second law for the blue block, which I actually pre-created to save some time. I don't want to spend too much time on it. So therefore, I'm going to show you both laws which are pre-created. Okay. So as you see, the brown block is controlled by this sketch. It's going to go up by 200 millimeters, stay put, and then go down. And the blue block will stay put while the brown block is moving and then start accelerating. Okay, so it's all preset. Now we can go into commands, and there is an option link. Okay, so it says creates a law link to a sketch. Well, I'm going to click link, and I'll select that sketch. Okay, and the maximum time, I think I wanted to simulate over 100 seconds. Okay, so it says a new kinematics law has been successfully created. So far, so good. And I need to do the same for the second one. So I'm going to click on the second command, again, link, select the second sketch. So that's another law has been created. And I'm all set. Well, let's check it out how it behaves. Okay, so I'll just collapse the tree for clarity. Okay. Need to go back to the kinematics workbench. Okay. And the simulation with laws, I'll use, let's say I'm going to make a very slow simulation to begin with. Actually, I'll start with the fast, which is 200. Okay. See, blows up. The second one. Okay, just make it slower so you can see it a lot easier. Let's say I'll make 1,000 steps. Reset. So you see the brown block starts going up, but the blue block stays put. It's not moving. Then both are stationary, and then the blue block slightly, slowly starts accelerating and going up according to the constant acceleration law. Okay, now just one more time. Okay, see this one goes up, stays put, and the second one starts moving faster and faster and faster, and it keeps climbing up, and at some point the brown block starts moving down. Okay, so that is the second way using two-dimensional curves. The third way is, or the third method is when you use imported functions. Okay, and I'm going to use this example. This will be a car roof mechanism, and the motion laws are defined in a tabulated form in external file txt. Okay, I want to show you this file real quick. Okay, that's pretty much what it is. This is comment symbol. Then there's a description for the columns. It's all contained in CATIA documentation, as we also teach it in our kinematics class. So there's interpolation, polyline, units, scale, and it's just a table. Can you do it using Excel? For some odd reason, no, it's only text file. And the columns must be tab separated. That's the way it is. All right, anyway, let me try to use this law now. I'm gonna go into that model. Okay, and when I double click on any command, I will see this option import. So it says create laws from a file. All right, let me select that. I'll select the roof laws. Hit open, and it tells me, yeah, everything was good. 4 laws have been created for the following commands. Okay, so just one import create laws, and the way how it works, it does the name matching. Okay, so as you see over here, the names for the commands like lead rotation, C-pillar rotation, they match the column names right here. Okay, that's how CATIA knows which columns to use for which command. So the first column is time. Okay, the second will be C-pillar rotation. The third column is roof rotation. The fourth is roof translation, and the last one is lead rotation. So if I click display file analysis, it tells me, yeah, everything was good. 4 laws will be computed, shows me the table, revisit the units, interpolation time, and so on and so forth. And I can actually visualize the laws. Okay. So the color coded, the C-pillar rotation is controlled by the kind of yellowish curve, which is right here. The lead rotation is the purple pink curve, and there are a couple others. All right, so far so good. Let's try to do a simulation. Okay, I'm gonna go simulation with laws. Just want to collapse the tree so it's easier to see what's going on. All right, and very slow, you see the leaves moving. Okay, then the glass and the roof, then the roof starts folding and everything goes in. Just like that, just almost like in real life. Okay, I'll run the simulation just one more time. We'll reset. Okay, see the first part is moving according to its law. The other 2 parts starts moving as well. Okay, so just using the same parameter time, kinematic time, I'm able to control motion of many parts using their commands. Okay. And I'm going to run just one more now faster before we move on to the next example. Okay. I want to show you what happens in the tree. So in case you're curious, see when they did the import, CATIA automatically actually created the part. You see it says kinematics laws for retractable hardtop, roof, etc. If I unhide it, see these are those curves which have been created actually as sketches and laws. So basically, this tool or this method kind of bypasses manual sketch definition, and instead you just create a table, put it into a text file, it imports, create the sketches, create the laws, and does it all seamlessly and behind the scenes. Very nice option. However, all this sketching stuff has its own limitation, which brings me to a third example. Okay, actually 4th example. All right, which is, let's say what I want to do is simulate the motion of a pendulum. If you go online and look for the motion description, it's a sinusoidal function, sine wave. So essentially the angle of the pendulum is determined as amplitude, which is swing amplitude, times sine. Omega is the cyclical frequency, t is time, and phi is phase. So if you use frequency in hertz, the formula changes like that. So that should be a sine wave. How do you sketch a sinusoidal function in the sketcher? The answer is you can't. So you have to use some other means, which is I call equation-based laws or symbolical laws to make that happen. So I'm going to do an example with this pendulum, and let's say what I want to do is to have amplitude of swing is 30 degrees. Frequency of swing is 1 Hertz, which is one full oscillation in 1 second, and the phase half a pi, so it starts at leftmost position. If I do that, my angle or my law will be like that: 30 times sine twice pi times 1 times t minus pi half a pi. So basically that's the law I need to create. Again, could I sketch it? I couldn't, so I have to use some other means. Okay, so let me go to that model and I will take a look at it. Okay, so here's a pendulum, there's a mechanism. There's only one command, so it seems to be suitable to be simulated using commands. The problem is I can't really simulate proper motion. With the simple simulation with commands, it's only linear motion, like that. Okay. So instead, I'm going to have to use something else. All right, and to do that, I need to create a law. So right here at the bottom, where you see the design table, there is a law option. It's not a sketch law, it's kind of symbolic or analytical law, okay? And what I need to do is essentially write down a function or equation, okay? And the one I want to write down in here is shown right there. All right, so I need to introduce a couple of parameters. These are both so-called formal parameters. We teach this topic, creating those laws, in the CATIA knowledge aware class. I'm going to go real, and I'll call it letter A. That's going to be the angle. Okay, so that's a swing angle of the pendulum. Another time real, and that's going to be the angle, not the angle, the time. I'm going to call it T. Okay, and I need to write down my law over here. Okay, so that's A as an angle is going to be equal, okay, 30, which is the swing amplitude, 30 degrees, right, times. And if I expand, I need to find the sine function, and here it is. So it takes real number in, and it gives me real number or decimal point number back. I'm going to just double click on it, okay. Now I need to populate what's in the middle over here, okay, and it was twice the pi, and the pi number is located in constants. Yeah, here's the pi. I don't even have to type it, I just need double click, okay, and that's going to be times p. Okay, now this is time value. We need to convert it to a real number without units, and we do it by using this very simple trick, which is we're going to multiply it by 1 radian. Okay. Now we need to introduce the phase, which is, again, I need the pi. Now half a pi, which is 90 degrees. Okay, and times 1 radian. Okay, so this gives me angle. This gives me angle as well. This computes the value of the sine given the angle, and 30 degrees is the amplitude of oscillation. Okay, but now how do I use this law in the command? Well, I need to use a formula. Okay, I'm going to right click edit formula, and over here, if you look at the dictionary, we can actually use evaluate function to evaluate the value of the law. Well, that's what I want to use. So double click goes in which law I want to evaluate. I'll use the one I pre-created, they're the same. Okay, and now I need to grab my time, right? The time parameter. So I'll click on the mechanism. That's your kin time. Okay, so that's a time value, but if I look at the law function, you see it needs real, which is without units. So to make it dimensionless or unitless, I need to divide it by 1 second. Okay, and the result, which is what this function returns, may need to be converted back into degrees. Okay, when you work with all formulas and relations, CATIA, you really have to be careful with units. If you use a parameter without units, which is type real, CATIA will interpret it accordingly to the international system of units. So your length will be interpreted in meters, not millimeters. Your angles would be interpreted in radians, not degrees, and the list goes on and on. So you really have to be careful here. All right, and I think I'm pretty much done. Okay, so again, if you take a look at the tree, you see there's a formula created, and it controls the command .1 value, which is the angle, swing angle of the pendulum. Well, let's try simulation with loss. Okay, you see it starts at -30 value. Okay, and when I start a simulation, there it starts swinging. Okay, now that's an actual sine wave motion. That's not some kind of a manual dragging the slider, etc. No, it's not like that. It actually simulates the actual motion given the law that we have written. Okay, I'll make it another one, just like it a little slower. Okay, yeah, that's your motion. Can I simulate friction so the amplitude slowly goes down? Unfortunately not. And when you talk kinematics, what it means as opposed to dynamics is that in kinematic simulation, the forces are not taken into account, they're ignored. So there is no inertial force, there is no friction force, it's just kinematic simulation without introduction of any forces in the mechanism. All right, so just to summarize what I've shown you, so when you want to run a simulation in your mechanism using just one parameter, kinematics time, you need to link kin time to all your commands. And there are 4 general methods how you do that. You can use formulas, which I did in my first example. You can use 2-dimensional curves such as sketches. That's actually a very nice option because it's very visual, and we as engineers like seeing things. You can use also tables, which is import from file. And lastly, you can actually use mathematical equations or symbolic laws. That's the most advanced option, which is typically overlooked by most CATIA kinematics users, but it's a nice one. All right, so that's pretty much all I wanted to show you, short and sweet. So we as a company offer training on those options you've seen. It's covered in DMU kinematics, and also if you're curious about formulas and laws and other entities, such as those, we cover them in the knowledge aware class, knowledge advisor and knowledge expert.